Hello, welcome. In this lecture, I am going to discuss about spherical polar coordinates. Okay, what are the different types of coordinate systems that we use in quantum mechanics? Okay, so types of coordinate systems that we use in quantum mechanics. Actually, we have 4 different types. Number 1, Cartesian coordinate. Cartesian coordinate system, also called rectangular coordinate system. Number 2, spherical polar coordinate system. Number 3, confocal ellipsoidal coordinate system. Then we have cylindrical polar coordinate system. Cylindrical polar coordinate system. Okay, so we actually have 4 different types of coordinate system. What I am going to discuss in this lecture is about spherical polar coordinate. Okay, because often we use spherical polar coordinate in the place of Cartesian coordinate to solve Schrodinger equations. So in this lecture I am going to focus only on spherical polar coordinates. Right. So let's get started. Before going to discuss spherical polar coordinate, okay, what is meant by Cartesian coordinate? In a 3-dimensional space, suppose I take 3 perpendicular axes, okay, x-axis, positive x-axis, this is positive y, and this is positive z-axis. Okay, in a 3-dimensional space, right? Let us represent a point. Some point, you take some point P. Okay, I am going to represent this point using Cartesian coordinate system. What is that? It's nothing but this point has some value of x, some value of y, some value of z. Okay, what is x, what is y, what is z? Very simple. You draw a perpendicular from the point to the positive z-axis or z-axis. Okay, that value gives you z. Right, then what about x and y? Just draw a perpendicular to the xy plane. Okay, draw a perpendicular to the xy plane, let it be p prime. Then from this point draw perpendicular line to the x-axis and perpendicular line to the y-axis. Okay, the point where this perpendicular line meets the x-axis gives you the value of x, and the point where the perpendicular line meets the y-axis gives you the value of y. Okay, this is the meaning for x, y, z, right, in Cartesian coordinate space. Okay, then one more information I like to give here. In quantum mechanics, we usually find a volume element. Okay, what is the volume element in a Cartesian coordinate space? Right, so this is the origin. Suppose I'll take a small volume element here. Small volume element. Okay, this volume element has some x length, let it be dx, some y length, okay, let it be dy. So this is dx, this length, and this length is actually dy, and the height is dz. Okay, so the side lengths of this small cube is dx, dy, and dz. Dx is nothing but distance along x-axis, dy is distance, the length of the side along y-axis. dz is the length of the side along z-axis. Okay, and here let us assume that this dx, dy and dz, these values are infinitesimally small values, very very small. So that we call this volume, we call this small space as volume element. Volume element. Volume element means it is the small volume, okay, occupied by a cube, right, in three-dimensional space, right? And volume element, the volume of this small cube we represent by the symbol d tau. D tau means volume element. Okay, how to calculate the volume element in Cartesian coordinate space? In Cartesian coordinate, okay, volume element is given as the product of dx into dy into dz. D tau is equal to dx into dy into dz. This gives you the volume of that small volume element. Okay, or the volume of the small cube that is present in the three-dimensional space, three-dimensional Cartesian space. Okay, now let's move on to spherical polar coordinate. What is spherical polar coordinate? See, whenever the system has a circular symmetry or a spherical symmetry, then we can use this the idea of a spherical polar coordinate instead of Cartesian coordinate. Okay, so when we use this spherical polar coordinate system, whenever the system has cylindrical symmetry, circular symmetry, whenever the system has a circular symmetry, suppose you might have seen the problem particle on a ring. Okay, particle on a ring is nothing but circular symmetry, and particle on a sphere can be considered as the spherical symmetry. So whenever system has circular symmetry or spherical symmetry, then we use spherical polar coordinates instead of Cartesian coordinate. Okay, now how we represent a point in spherical polar coordinate? Okay, see, I'll take 3 perpendicular axes here. So this is the positive x-axis, and this is positive y, and this is positive z, and this is the origin. Now I'll take some point P here, some point P in 3D space. Okay, and that point in Cartesian coordinate we represent that point using the values x, y, z. Okay, in Cartesian coordinate. In spherical polar coordinate we represent the point using the variables r, theta and phi. People call this as phi, okay, or sometimes phi. Okay, I am going to call this as phi, r, theta and phi. Okay, what is r, what is theta and what is phi? Okay, and how these spherical polar coordinates related with the Cartesian coordinates. We'll discuss that as we go along. So what I'm going to do, I'm going to connect the origin to this point. Okay, this line or the distance between origin to this point, okay, the length of this line is nothing but r. So what is r? R is nothing but distance between the point from the origin. Okay, then what is theta? Very simple, isn't it? Theta is the angle between the line connecting the origin to the point to the positive z-axis. So this angle is nothing but theta. Okay, so it is the angle between line joining the point to the origin and the positive z-axis. Okay, angle between these two lines is what we call as theta. Then what is phi angle? What you have to do for phi angle, you draw a perpendicular from the point P to the XY plane, also called as projection. Okay, I'm just projecting this point to the XY plane. Now connect the origin to this point P prime. Okay, now the angle between this line, that is the line joining origin to the projected point P prime, okay, and the positive x-axis, this angle, between these two lines is what we call as phi. Okay, so keep this in mind. What is phi? Phi is nothing but the angle between positive x-axis and the line joining the origin and the projected point in xy plane. Okay, this angle is called phi angle. Okay, now, so these are the variables r, theta, phi are called spherical polar coordinate variables. Okay, now what I'm going to do is that what is the relation between this r, theta, phi and x, y, z. Okay, yes, we can find the relation by making use of some trigonometric properties or triangle properties. Okay, yes, very simple how to do that. Okay, first I'll join the point P to the z-axis. I'll draw a line from the point P, perpendicular line. Okay, draw a perpendicular line from point P to the z-axis. Okay, it may join the point may or the line may join to the positive z-axis or negative z-axis, whatever it is. You draw a perpendicular line from the point P to the z-axis. Whatever value of z we get here, and that is the value of, that is the length of this, okay, from 0 to that point, and that length is z. Now, so this length is z. I'll take this triangle O, P, and let's take this point as A. Right? So in triangle, observe carefully, in triangle O, P, A. In triangle O, P, A, so this here we have the angle, and this is opposite side, and this is adjacent side, and this is hypotenuse. So adjacent side length is z, hypotenuse length is r. Now what is the theta, or what is the function that connect the adjacent and hypotenuse? Is the cos theta. So cos theta is equal to adjacent side, that is z, by hypotenuse, that is r. So what is that? Z is equal to r into cos theta. Okay, this is the first relation. This is a relation between z and the spherical polar coordinate. Z is equal to r cos theta. Okay, then what about x and y? Right? See what I'm going to do for x and y here from this point P. Okay, and or I'll take this triangle O, P, P prime. Observe carefully, O, P, P prime. Here we have 90 degree, and if this is theta, this is also theta. Why? Because these two lines are parallel. Okay, line O, the z-axis, and P, P prime. These two lines are parallel to each other. Therefore, if you draw any line connecting this line and this line, okay, then this angle and that angle should be same. This property relation. Okay, so now here we have the angle. So this side is the opposite side, right? And this is the hypotenuse. Now, which angle connecting the opposite side and hypotenuse is sin theta. Okay, so next in triangle O, P, P prime. Okay, in triangle O, P, P prime, what is sin theta? Sin theta equal to opposite side. Opposite side is nothing but OP prime divided by hypotenuse. Hypotenuse is R. So what is OP prime? OP prime is equal to R into sin theta. Okay, now we have got the value of this length. Okay, now what I'm going to do, I'll join, I'll draw a line from point P prime to the, I'll draw a perpendicular line from the point P prime to the x-axis. Okay, to the x-axis. Okay, now we get a triangle here. Okay, we get a triangle here. This is the value of this length is x. Okay, I'll take this point as say B and this point as C. Okay, this point is already there, P prime. Okay, now I'll take the triangle OBP prime. In this triangle, so here we have angle, so this is the opposite side. Okay, and this angle is a 90 degree, and so this is the hypotenuse. OP prime is hypotenuse. Okay, so in triangle OBP prime, here, in triangle OBP prime, okay, this side is adjacent, this is opposite side, so this side is adjacent. The value of adjacent side is x and the value of hypotenuse is OP prime. Okay, so the angle which connect these two is sin phi. So what is sin phi? So adjacent side, I'm sorry, cos phi. So what is cos phi? Cos phi is equal to adjacent side, which is nothing but this length x. Then hypotenuse is nothing but OP prime. We got the OP prime value already, so let me put that value as such. Cos phi equal to x by r sin theta. Therefore, what is x? X is equal to r sin theta cos phi. This is the relationship between the coordinate, the Cartesian coordinate x and the spherical polar coordinates. Okay, then I'll take the same triangle. See, I'll draw a perpendicular from P prime to the y-axis. Okay, it makes a point on y-axis. Let me take that value as c. This length OC is nothing but y, and you know very well the length OC and the length BP prime are one and the same. So if this is y, this is also y. Okay, therefore we can find the value of y by making use of the same triangle OBP prime. Okay, so I'll use the same triangle. In triangle OBP prime, what is sin phi? Sin phi is nothing but opposite side by adjacent side. Opposite side by hypotenuse. Now opposite side is y. Okay, so this is phi. The opposite side is y, and the hypotenuse is nothing but OP prime. So sin phi is equal to opposite side y by the hypotenuse, that is OP prime. And you know the value of OP prime, which is r sin theta. Substitute that value here, so we get sin phi equal to y by r sin theta. So what is y then? Y is equal to r sin theta into sin phi. Okay, so this is the relation between the Cartesian coordinate y with the spherical polar coordinate r theta phi. Okay, now I'll just summarize all these coordinate values. Okay, so what is the relation between x, y, z with the spherical polar coordinate? X is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. Okay, so this is the relationship between x, y, z with the spherical polar coordinate. Okay, then. So if x value, y value, z values are given, you can calculate the value of r theta as well as phi. How? So what I'm going to do, first let me square these values and I'll add them. So x square plus y square plus z square. Okay, take the square of these values, then add them. If I take square of this, I'll get r square sin square theta into cos square phi plus the second value. If I take the square of this, I'll get r square sin square theta into sin square phi plus the last one r square cos square theta. Okay, now I'll take the first two terms, and in the first two terms I'll take r square sin square theta as common. So I'll get r square sin square theta. If we take it as common, we get cos square phi is remaining here in the first term, and sine square phi is remaining in the second term. Plus keep this r square cos square theta term as such. And you know cos square phi plus sine square phi, the value of this summation is 1. Therefore, this is equal to 1. This value equal to 1. Therefore, you get r square sine square theta plus r square cos square theta. If I take r square as common here, I can write this as r square. If I take it as common, I'll get sine square theta plus cos square theta. Sum of these two is nothing but 1. This is also equal to 1. Therefore, r square. So, x square plus y square plus z square equal to r square. Right? Then what is r? R is equal to square root of this. Okay? R equal to square root of x square plus y square plus z square. So, if Cartesian coordinates are given, x value, y value, z values are given, take the squares of those values, add them, then take square root. Okay, that value is nothing but the r value. Okay, so from Cartesian coordinates, we can find the value of r by making use of this relation. Okay, then if I divide y by x, what we get? X relation. If I divide y by x, what we get? What is y? Y is nothing but r sin theta sin phi. And what is x? X is nothing but r sin theta cos phi. This is x. So r cancel, sin theta cancel. I'll get sin phi by cos phi. Sin phi by cos phi is nothing but tan phi. Therefore, I can write tan phi equal to y by x, or phi equal to tan inverse of y by x. Very simple. So you can find the value of r, you can find the value of phi by using the value of x and y. Once you know these two values, you can calculate the value of theta by making use of this. That is, you know, z is equal to r cos theta. Okay, if you know the value of z and if you know the value of r, then using these two values, you can calculate the value of theta. Okay, so you can convert Cartesian coordinates into spherical polar coordinate by making use of this. Okay, then before completing this lecture, I'll give one more information. See, dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Okay, we call this as an operator called Laplacian operator. This is Laplacian operator in Cartesian coordinate. What is the corresponding Laplacian operator in spherical polar coordinate? By using chain rule, okay, we can find these values. I'm not going to do that in this lecture, but it is quite easy only. Okay, little time consuming, but it is easy. So what we have to do, using chain rule, you calculate this, you calculate this, you calculate this, then add them. So what we'll get is del square equal to 1 by r square into dou by dou r into r square dou by dou r plus 1 by r square into sin theta into dou by dou theta into sin theta dou by dou theta plus, I'll write here 1 by r square sin square theta into dou square by dou phi square. Okay, so this gives you the expression for the Laplacian operator in spherical polar coordinate. Okay, yeah, I stop here. In the next lecture, we'll discuss about Jacobian. Okay, the Jacobian determinant and some of the applications of Jacobian determinant. Yeah. Yes, I stop here. Thank you. Thank you for listening.